It's okay.
Any question?
Oh yeah, I was wondering if we could go over a few of the homework assignments that I had some questions on.
Which one? Yeah.
I had a question on 5A and 5B.
5A and the 5B. Okay. Five A. 5A is. I think this one is differential. This one, yes. This one I told you
Right.
that there's a lab you can actually look at it and then redo it, follow the formula, right? Remember that?
Right. I'm still a little bit uncertain about the matrices I was setting up. I'm not too sure if I did it right.
So you want to show me?
Yeah, could I? It says screen sharing is disabled.
Let me try, okay? One moment. I think that's because that default setting is don't allow. I actually opened it now. Okay, you can share screen now. You should be able to share now.
Can you see my screen now?
Yes, I can see your screen. Yes.
Okay, so these matrices, D and T, I was kind of a little confused on setting up. I think I figured out T based off of like the example. Um, but I'm still not too certain on how to set up this G
D
matrix.
is rotational, right?
Uh-huh.
D is rotation, T is transition. W is your the observed speed on the observed frame, frame, right? So, and then move that, let me see. UT equals ND array. You reshape it to 4, Why you need to reshape? Why do you need to reshape to 4?
Um, I don't know. I think I saw that in an example, but I guess it's not
Yeah,
necessary
not
because
necessary because you already 4.
Mhm.
Yeah, that should be all right. Should be all right. You run it and see. Oh, you already had the readout. Okay. The number I think maybe off. I'm not sure where it is off. Maybe your D is. Maybe your D has something you need to check your D matrix. I think it's your D matrix. It's your D matrix. You need to check the number in D matrix, okay? Your setup should be okay, but your D matrix, you have to check your D matrix. The after overall numbers is actually not right. But it's
Uh-huh.
okay. I won't deduct point, okay? Bottom line is something like this. I usually don't deduct point from you, okay?
Okay.
But you are in the PowerShell, okay? You're in the PowerShell. So if you want to change the PowerShell, okay? If you want to change the PowerShell, you want to go to the normal command, you should come over here, do Control Shift P, okay? And then you say, I'm sorry. I'm sorry. Okay. Actually exit full screen mode. Okay, here let's actually go to here. Profile. So terminal select default profile. Okay, you say command prompt. Okay, and this one you actually close your terminal. Okay, you actually new a terminal, and that new terminal now will be normal C drive instead of PowerShell. Okay, because sometimes the file you created by the PowerShell you cannot access it later because of the super user permission. Okay, by button 9, you just need to check your matrix numbers, should be fine. It's okay?
Yeah, I guess the thing I'm just still stuck on, I think, is coming up with the matrix numbers.
Mm-hmm.
I was looking back in like the kinematics video to try to like refresh on it.
Mm-hmm.
And I still think I'm just a little confused on it.
You are still confused.
All right.
This one here, what I saw here, it actually you do have a displacement, but we only have the speed on the rotational part for the D position, right? So I'm not sure where this one is from. So, and this is hard to, okay, let me see. Okay, let's go back into this differential. Let's see, differential metric kinematic. Okay. So the whole session is to prepare for your differential transform metric, including the rotational part and the displacement part. Okay. So overall, when you actually do coding, this one is for the number that using the 2 radians. So you use 2 radian, you are wrong because the speed is different in what we have there. This was 2 radian per second. But the problem you have is not 2 radian per second. This one is this. This is just for this metric. This metric is by the example. It's not the homework you are working on. Is okay? It's not the homework you're working on. This one just the number for this 2 radian and this. Okay. So this 2 radian speed is 2 radian per second. 2 radian per second is actually your 2 is the rotational along the z-axis. Along the z-axis, okay. I'm sorry. Here actually is xy. Okay, this one is actually you have xy plane and your rotation is over here. You do have the omega g. Okay. So because of that, you plug in those numbers into the metric here. Let me see. Now this one. This one. So it's actually the -2 plus 2 is from here. This is the rotational metric here. That's why here you have -2 and 2. But the one you are working on right now is not 2, it's 3. The one on the homework is 3, it's not 2. So I say your number is wrong. Your number is wrong because here is 3 radian per second. right? It's not 2. So your 2, you just copy from the example, but you did not apply this one to there. It's still G translation. So G is the speed you have on the G axis here and here. Is that okay?
I get it now. Thank you.
Okay, so that's this velocity one. And the other one is your displacement. You have 2, 3. 2, 3 is the transitional part. It is the location here. You have a displacement of 2, 3. That's the reference place distance or displacement. Okay, so here it's just like you do have this one, it rotate in this direction, but this friend over here, it actually is not changing. It's still always at the 2, 3, 0 location, but your friend is rotating. Your friend 0 is rotating. So your observed friend, actually number should be changing, something like that. Okay, but anyway, this one's the 2, 3 number is from the coordinate of this point. But go back to here. U is 4, 3. It's a different one. Is okay?
Yes.
Okay. And your W actually, your V is here. Your V and W is actually, there is a vector moving at the speed of this one over here, according to here, with respect to here. And we want to observe from a rotating frame to see where they are. You know what I'm saying? So that's what we want to do. And then you need to go back to the, okay. So that's what we have here. So here you do have a point relative to the C frame. Okay, 3, 5. And actually this 3, 5 actually is having the speed of 230. 230 is the speed of the point. Okay, it's actually the W is 23. Okay. I'm sorry, this is the reference point. And your W is by this W number, the vector. Okay? Is that okay so far? So you cannot just use this one. Okay, I think I have the reshape is okay. Just guarantee that it is going to the overall format. Okay? But here is a 3 by 3 by is the coordinate you have here. 3 by is the coordinate here. Does that make sense?
Yes.
Okay. So that's 3 by 0, 1. 0, 1. This one is the homogeneous vectors 1. Okay, that's extra 1. We just put it there. Okay. So this one, okay. Now let's look at 5B. Okay, let's look at 5B. Is that okay for so far?
Yes, I think so.
5B. 5B, it actually is gonna be Hardenburg table and then create gonna be Hardenburg's metric. So this one is 2. Okay, 2 degree of freedom manipulator. So it actually is something like this guy is rotating, this guy is extending in this direction. So it's something like here you do have something that rotate, and then here you do have a cup, and it go up and go down, right? This is somewhat like a Dumbo. If you go to Disneyland, there's a Dumbo, right? Dumbo our coffee cup. You know what I'm saying? You know what I'm saying? This
Repeat.
actually, if you go to Disneyland, I don't know whether you've been there before or not. Disneyland, and there is a flying tumble, okay? DUM, I'm sorry. Name of the elephant. So it's something like this, right? It's like a merry-go-round, but actually what happened is that you do have something in the middle that's for rotating, and then there's a bar. And okay, this is actually 3D, so it's actually vertical going up and down here. You know what I'm saying? But this one actually is a bar going up and down. But the one that we are modeling actually is similar to this one. Okay, that actually is similar to the tumble. It's just like you are rotating over here, and then the tumble go up down here, right? Is that okay so far? So this one totally you have 3 frame, 2 join 2 frame, right? So 2 join 3 frame, and you need to actually creating the then there'll be Hardenburg table, and then do modeling and do program on it. Okay, so there's a so-called rotate revolute join, and one is standard up. Okay, and the operation is similar to tumble. Tumble actually is 1 bar, but it's not. It's a fixed bar, but the cup is actually going up or down. Okay, so it's actually a little bit different. But something like this. Okay, something like this. Okay. Anyway, this one you kind of need to look into the procedure to find the so-called Hardenburg metric, and then plug in. So there is next one B7. So B7, there is a lab. Okay, you should be able to find this Hardenburg one. The whole series is over here. You kind of need to extract your Hardenburg table, because they are 3 frame. There are 2 transitions. So actually, it's also 2 row you need to create. 2 row you need to create. Okay, and then you need to based on the rule to generate the theta, alpha, R, and D. Sometimes R is also called A. Okay, the S movement. So based on your kinematic diagram, you kind of try to find your theta on the both frame. Try to find your alpha on the both frame. Try to find the R or A, sometimes this one is A, on the 2 frame. And on the spread, two transition metric. Okay. So basically you have 3 frame, that means 2 row. 4 frame, 3 row. 3 frame, 2 row. 5 frame, 4 row. Okay. Number of row is 1 minus the frame. Frame minus 1. Is that okay? And as for the generation of the table, your row number 1 should be generated by your join a frame number 1 and frame number 2. You use frame number 1 and frame number 2's difference to generate the 4 parameters. Then your frame 1 to frame 2 will generate the second row. And once you get the row, plug in into the Hardenburg program, you should get a metric. So there's a Hardenburg metric. You can directly just call the function and pass the parameter in, and you should be able to get it. Is that okay?
I think so. I'm still a little confused with the table. I guess the only thing is when I was making my table, and this is where I think I'm messing up, is I had um like 3 different rows, but we would only need 2 rows, you're saying?
Yes, you have. Okay, so they are 2 join 3 frame, right? 2 join 3 frame. So basically, you only have 2 row. 2 row, you have 3 frame, because right here, say, let's assume that you are trying to create the first row. First row's theta is based on the x0 and x1 to g0. So basically, you use two friends of property to compare to generate one row. So if you actually try to create second row, you are using x1 and then actually x2 and the g1 to generate second theta. It's actually between second frame, frame 1 and frame 2. So you use frame 0 and frame 1 to generate the row 1. You use frame 1 and frame 2 to generate row 2. So 3 frame, 2 row. Is that okay?
Yes, I get it now.
Okay. And as for how you can extract it, there are 4 rules you have to study. Is that okay? 4 rules. So it's a detail. One by one, it's actually in detail. It basically just teach you how to compensate for the angle. Okay? Or how to compensate for the extender. Does that make sense? And then once
Yes,
you
I think so.
get the table, plug into the function and call it. That's it. Okay, that's it. Okay. You see, all these, okay, all these genetic diagram, these slices I generate by myself. So all these are handcraft. I draw it. Okay, nobody give me this diagram. I need to draw it one by one. It take a long time and take also make the videos. Take quite a while to do it. Okay. But you have to go through it once by yourself. Okay. I don't want to teach you, oh, okay, this is how you compare it. Okay. That you have to go through it by yourself. Then you will learn. Okay. If you still have question, I can answer you how it can be done. But before that, before you ask question, I would rather you go through it by yourself. Okay.
Yes, I have looked through the slides in the video.
Which one?
I was still just confused on it, but I think I get it more now.
Okay. Go through it one more time.
Okay.
See if you still have question, you still can come back. Okay.
Okay. Thank you.
Okay. No problem. Other questions? Okay.
I don't think I have another question.
Okay. Just try to. I mean, as you can see, we actually focus on the modeling. Okay, focus on modeling. Hope that you do pick up the math, pick up the programming. Okay, and this programming will be useful later when you actually work on a lot of these frame transitions. Okay, very useful. Okay. Okay, and let's. Any other question? Okay, no question. I briefly go through the lecture 14 control loop. Okay, so we talk about a manipulator. So manipulator is that you have some control variable to control your manipulator. Those are controlled by the robot, controlled by the theta and data theta, and also displacement. Okay, whatever. Then you have feedback loop, and you have a feedback loop. You may have 2 feedback loops. One feedback loop is on your vehicle that move your robot. The other feedback loop is on your robot arm to precisely control your robot arm. So 2 loops are separate. Okay, we both call them motion loop, and they are in the control system. So control system right now, this is more like a hardware. more like hardware. Eventually, you go more like hardware. Okay, so the previous few chapters they are more mathematical model, more homework. So this portion is supposed to be more hardware oriented, but we are online course. We are online course, so it's impossible that we have a lab, physical lab to have everybody to build microprocessor and controller. Originally, we discussed it, but the possibility is pretty slim, so we give up. Okay, so you can see that some of the video I do show how to build a robot. I have my son build a robot for this course, but eventually we give up. Okay, because it's not feasible. We cannot provide a robot for everyone to do. So instead of doing that, we actually have students to build their own project on robot. Okay, that's why we have the project doing that. But basically here, we still want to introduce the robot control. We still want to introduce the robot control. So robot control, one is open loop. Open loop is there's no feedback. And the other type is called feedback control. Okay, so feedback control, you do have feedback. And then they are high-level control system paradigm, model plan approach, behavioral approach, finite state machine approach, and low-level control loop. Low-level control loop is actually for motor velocity control, PID. Okay, PID actually proportional integrate differential. PID means proportional integrate differential controller. Okay, these are typical control loop, not only for robot, but for any general control as well. Okay, so we are talking about this different control loop, but I think that today here we are looking at right now, it's more of the low level loop. Okay, the PID loop. Okay, so that's why I highlighted the low level loop. So let's look at this loop. Okay, so you do have some system variable U you want to control. The U you want to control is your control variable. Okay, so there is a control variable, say theta or something. You actually create a displacement. So this one is the control variable. This one is the physical displacement. Okay, or observe the location. Okay, and you feedback that to your path and then estimate the error and then using PID control to control it. So PID control, you can look at it. This one actually you can be proportional, can be integrated, it can be differential. This just kind of providing a filter for the error estimation. So error can accumulate, error can be highlighted, error can be proportionally amplified to using this PID, depending on which one you use. Okay, depending on which one you use. So very simple one is a simple up-down controller, 0-1 up-down controller. That's the simplest control. Okay, then you can have the proportional. You have the proportional integrate, proportional differential, and proportional integrate differential controller. These different controller just to provide different filter effect on the control variable. Okay, and because of the control variables, control filters difference, you would have different time for reaching the stability. So proportional one, you can see that there is actually slower to reach the stability, and there's a systematical error there. Okay, it doesn't reach the one you want to have. This green one, proportional differential, also have some standard error. You don't go back to one. Okay, you don't go back to one. And if you have the integral, they will have no such error. But it will smooth out the design, and it actually is slowly. The time to catch up the control loop actually is slower. Okay, so different filter the time domain and frequency domain response for the step response will be different. Okay. Okay, so here we do provide different PID simulator, and you can pick. There's no right or wrong. It's just like which kind of design you want to have. Okay. And here we do have a PID controllers model, okay, in there, and we are mimicking there is a step response coming in, and then how fast you can catch up, okay. So based on different K numbers, different your proportional constant, K is proportional constant. The K, you have different K numbers and different parameters, you will end up with different response, okay. And there's some damping factor. Damping is no good, okay, but sometimes overshoot or undershoot, if it's well controlled, it's okay. A little bit of the overshoot or undershoot, by helping the loop to reach stability faster, is actually okay. Okay, and but damping too much, it may make the system not as comfortable. So it actually is some sort of study you want to have. Okay, so these are the mathematical model. So that controller is some kind of gauge, and you read the gauge, you feedback to control how much gas you need to provide. So this one is a feedback loop. Okay, this one is a feedback loop. So that's a low-level feedback loop. We do have an open loop, closed loop, proportional controller, proportional derivative controller. Okay, this different loop. So here let's look at how we set a motor to a given velocity. So we do have this motion control motor. Okay, so we want to have a desired speed, and we have observed speed, and you need to use a feedback to see how fast you will control the motor. Okay, so you have open loop. Open loop means that you just give the desired speed and see whether you can reach it or not, because there's no feedback. So you have no way to tell actually how fast it really is. You just have an input by output, input by output. So this is open loop control. Closed loop control is that you actually measure your actual speed and adjusting your controller to control your motor. Okay, so based on this, if you have no controller, okay, if you have no controller, then this one is actually just the open loop. Okay, just open loop, no controller. There is naive velocity to the mode. Okay, maybe the transfer curve is totally wrong, then you will set to the wrong speed. Okay, and slow rise time, and it may not reach the desired speed that you want. Okay, the next one is proportional controller. That means that you use the difference between your active your actual speed and your desired speed, and use a K amplifier to amplify it. But this problem is pure proportional controller, is that there's always a dead zone you will see that you can never catch up the real expected speed, okay? Because they are systematical difference. So there's a big error. And it may have an overshoot. It's faster in rise time because actually the K is an amplifier. You move faster, okay? So it's a fast, you may overshoot, and the rise time is bigger. Okay, so the overshoot is no good. Okay, gap is no good. Okay, and then because we don't want to have that overshoot, so we actually try to use differential PD. Okay, proportional derivative controller. This one still, because of derivative proportional one, it actually has amplifiers, so the rise time still faster, and the reduced overshoot, overshoot is reduced because you take derivative on it. But the problem is that the gap still exists. Okay, the gap still exists. Now next one, you actually proportional integral controller. So this one will accumulate the error, so that it will increase the overshoot, and then it will actually remove the error. Okay, remove the error term. But the best one would be the PID. Okay, you include the integral part and the differential part, and you will reach the desired speed. But this one the control is harder. Okay, bigger. Okay, so this one is a closed loop. Okay, this one's a closed loop system for this speed control using the PID. Okay, so let's see if you want to keep the straight line. Keep a straight line. You have a car. You do have right wheel. You do have left wheel. Okay, so if your right wheel move faster, and actually your left wheel moves slower, then your car will go left. Okay, your left wheel go faster, right wheel go slower, you will go right. Okay, by doing this, you can steering your car. Okay, you can steering your car, so you actually would control your trajectory, and then you will also control your velocity over time, left motor velocity and right motor velocity. Okay, so that's that. But you can actually use a PID to actually control it. Okay, and also be able to maintain closer to the straight line. Okay, closer to the straight line. So how do we make our robot go nice straightly? We actually will use a PID controller. Okay. Okay. So actually you have to you need to have couple of drive motors and then measure the speed and angles. Okay. Okay. So this one actually is the control loop diagram. And you set up that, and then they are different system equation for the different control loops. Okay, this mathematical term you can start it. Okay, so here this portion, I don't waste time to really talk about it too much. Okay, but basically, the control loop is you try to set up the control loop, and then you use a mathematical model to check its stability, time domain response, and also the overshoot undershoot condition. Okay, and is there this kind of the hysteresis curve? Okay, Smith trigger behavior. Okay, something like this. You have to study whether you actually can go back to the original state or not. Okay, and you can model it. Okay, and simple control, the simplest control is on-off. Speed up, slow down, speed up, slow down, slow down. And that's actually is digital control, okay? Digital stimulus control. Okay, that's on-off control. And also, sometimes we also call it charge pump. Charge pump to actually pump the data up or down. Okay. And after that, you can also use the analog integrator differential control. Okay. Anyway, this different equation you can set up, and then you enter the system, and then put that into electronic system to design. Okay. The integrator and the differential and the derivative system, they are filter design, and filter design by themselves. You can find the so-called RLC component. Okay, your resistance, inductive, or capacitive component to design your PID. If you use electronics, analog electronic system, and you can also put in all the control in digital loop and to control it. Okay, so nowadays people tend to use the microcontroller to perform this PID. Okay, so this chapter we just teach you how to design a low-level control loop. But in fact, this is a different control loop can be implemented by analog RLC circuit or be implemented by digital differential equations. Okay, it really depends on what technology you use. Okay, any question? Any questions so far? So I briefly go over this lecture, okay? Just to show you how to design a control loop. And some detail also, I don't go into the detail too much because I have the, you can watch the video. So the key point I'm trying to point it out here is that these different low-level control loop is the loop design that you want to have to control your variable. Would we actually really implement it in your car? And we would design the PID controller in analog approach or digital approach. Okay. And next talk, we are going to talk about the high level system controller. That's another level. Okay, that's another level. Any question? Any question?
I don't think so.
Okay, if no question, today we are up to here. Okay. Let me know if you still have questions. You can shoot me an email or Zoom me. Okay, I'm sorry. Send me by Facebook. I usually answer some question there. Okay. Is that okay?
Yes.
You know my Facebook, right?
No, what is it?
My Facebook is okay. Pretty simple. It's HTTP. Okay. Facebook.com/dr Dr. Eric Chung. Is that okay? This one, just Dr. Eric Chung. Okay, let me copy to the chat box. Office time maybe take longer, okay? Simple question, I'll type back to you. Any question? You got it?
Yes. I don't think I have another question right now.
Okay. So that's it for today, okay?
Okay, thank you.
See you next time. Bye-bye.